I'll post the answer key in the course links later today. Go ahead.
Then there's problems
that the first problem was mostly plugging numbers into equations from
the very first
lecture. And
you might
have discovered it's harder to get numbers that make sense than you thought because there's a lot of numerical facts to plug in. But I won't belabor this because you'll have to look at the key.
One of the main
things to note here, of course, is that the population difference between the alpha and beta states is quite small. And this is why NMR is so insensitive. And beating this, for example, is what D and T is for. Problem two is also putting numbers in. I'll let you look at that. Problem three is a problem
that one does over and over
again.
And that's calculate
the pulse length. Or calculate the V1 field. It goes both ways. But here, for example, in somebody has told you that you have a 25 kilohertz field, you want to know how long the pulse length is. So the on-resonance rotation would be omega 1 times the length of the pulse, and you want that to be pi over 2. And you're always going to be getting mixed up between hertz units, hertz and angular units. So this is an angular unit. So this needs to be pi over 2 over here in degrees. And then we can solve this for tau p. This is in angular units. But if I multiply by 2 over 2, I have 2 pi in the numerator, 4 in the denominator. Gamma V1 is an angular unit, so omega divided by 2 pi converts to hertz. So this becomes 1 over 4 nu 1, and that's 25 kilohertz, and I get 10 microseconds. If you work in hertz, 90 degrees is 1/4. 1/4 of 360 degrees. If you're working in hertz, you have to think in fractions of the circle. And if you think in angular units, you're thinking fractions of 2 pi. So a 90-degree pulse for angular units is pi over 2. A 90-degree pulse for hertz units is 1/4. This is a problem that if one understands this problem, one is in very good shape.
Your battery.
Oh, nice.
I don't want to go rummaging through that.
Well, if you do that,
you have to do some of the work.
So do we have any
volunteers for this problem? So we have in this a pulse that's off resonance by some amount. So we have an effective field, and we want to know where the magnetization, Z magnetization, ends up after that pulse.
And we
And we have multiple ways
of
of doing this. Our exact method
would
be to
rotate
the effective field
up
to the z-axis, which then rotates the magnetization z-axis off point in some other direction. Rotate that magnetization around the z-axis, and then rotate
everything back to the original
frame. So I'm somehow lost. Interesting.
Right when you need it most.
What's that?
Right when you need it most.
That's
So I forget
what were the how you say the offset was? Kilohertz.
So
here this was 3.2 kilohertz.
And here
the Omega 1 was 25 kilohertz.
And was it
along X or Y?
Okay.
So now
one way
of doing this, right, is we say that at angle theta. This is the x-axis. This is the y-axis.
So we
want to start by rotating around x by minus theta in order to bring the effective field up onto the everything's running out of that. Up onto the z-axis. And if I have z magnetization, and I rotate everything around x by minus theta. In my picture, I'd be rotating by plus theta. Then the z magnetization ends up on rotating towards minus y. So my initial z magnetization, we call it IZ for magnetization, will then go to IZ cosine theta minus IY sine theta. The z magnetization rotated towards the minus y-axis, while omega E rotated up to the z-axis. And then in step 2, I rotate the magnetization around the z-axis by the angle alpha, where alpha will be omega E times the length of the pulse. So nothing happens to IZ. I have IZ cosine theta, IY sine theta, cosine alpha, and then the minus IY magnetization will precess around Z to the plus IX axis. Minus IY rotates around Z towards plus IX. So we'll have plus IX sine theta sine alpha. If I draw a better picture of that. So after the first two transformations,
we have
IZ
cosine
cosine theta
minus
minus IY
sine
sine theta
cosine
cosine alpha
plus
plus IX sine theta sine alpha.
And
And now we have to rotate by
a
a
minus
minus
theta
rotation around X.
We
We started out by doing plus rotation around
X. We then did a rotation.
We then did the rotation around Z, and now we have to undo the first rotation to come back to the original frame.
So that means
So that means rotating around X
by
by minus theta.
So that
So we bring a maybe E back to where it started.
We have to
We have to rotate
by
by minus theta around the x-axis.
So what
happens to IZ? IZ
will be
will be cosine
squared
theta,
and
and then we'll rotate towards the plus y-axis. Cosine theta, sine theta.
the
The sine y magnetization
will be
will be an IY
sine
sine theta cosine theta cosine alpha,
and
and then
the
the
x
x
rotation
rotation
minus x rotation
will take minus IY plus IZ.
We have
We have magnetization of minus IY.
My
My thumb is along X,
will rotate up
plus
plus IZ.
to plus IZ.
And we'll have
So then we'll have
plus IZ
plus IZ sine squared theta cosine alpha.
And
And then
nothing
happens to the IX magnetization.
So
So I end up with plus IX sine theta cosine alpha,
or
or sine alpha.
And
And obviously I can combine the like terms, so I can add together the two IZ terms
and
and the two IY terms.
Maybe
There's some trig simplifications I can do.
But at
But at the end of the day,
I have three components of
magnetization.
I have the IX
I have the IX component, the IY
component,
component, the Z component.
So I can
So
draw
I can draw a picture of where the vector points
in
in
three
three
dimensions.
dimensions.
The
The amount of
IZ
IZ magnetization
is the
is the amount of magnetization that is left on the
Z.
Z-axis.
So that's
loss of signal. I would like to get all of the Z magnetization
into
into the
the
transverse plane.
So the
So the
off
resonance effect left some of the Z magnetization on the Z, some of the initial magnetization on the Z-axis.
and I can
I can look and see how, I can do the calculation then,
and see
and see how much that is.
The X and Y
The X and Y magnetization,
the vector
the
sum
vector sum of those
is how much
is how much transverse magnetization I have, how large my signal will be.
If I was
If I was on resonance,
the
the
Y
Y pulse
would have
would have put all of the
magnetization
magnetization onto the x-axis.
Now
I've generated some X magnetization and
Y magnetization.
some Y magnetization.
So I have a phase.
So I have a phasor
in the spectrum,
in the spectrum,
depending
on
how much
Y magnetization I have,
determines
determines how large that phasor
is
is going to be.
And I'll
And I'll need to phase correct that
at the
at
end.
the end of the day.
And now it's
Now
just
it's
a
just a matter of plugging in the numbers,
calculating
theta, calculating alpha,
and
doing all the trig calculations.
The other way
of
of doing the problem,
an
approximate
approximate way
is we have This
situation, 3.2 kilohertz offset
and
and 25
25
kilohertz
B1.
B1 field. So that's close to,
our
our effective field isn't tipped away very far from the transverse plane.
So we
So we said in that case,
we could
we can
approximate
approximate the pulse
as
as
a short
a short delay,
an
an
ideal
ideal
pulse
pulse
of rotation
of
alpha,
rotation
and then
alpha,
another short
and then
delay.
another short delay.
So if we start with IZ,
So if we start with IZ magnetization,
nothing happens
during this delay,
and then we
apply
the next
the next pulse of angle, rotation angle alpha. So
we
we have IZ goes to IZ,
cosine alpha minus
IY
sine alpha.
and
now
this is followed by this correction term.
Nothing
happens to IZ. IY cosine tau core times the chemical shift,
and
and then
minus
IY rotates towards plus IX, so plus IX sine alpha sine tau C omega.
and
Tau C,
back
in the notes, tau core was 2 times the length of the pulse over pi, what we worked out at some point in the notes.
And now we could plug
the numbers in and see how different this approximate calculation is
from the
from the exact calculation that we did. And
for this
range of offsets, this is extremely close to the exact calculation, and much more convenient.
So
Questions about this problem? And this is being able to work out a problem like this is extremely important. We want to make sure we want to understand the steps and the reasoning. It's worked out in gory detail in the answer key. Everybody happy if we go on? Now I really need to figure out how to get back. Nice. Now I got myself into trouble. That worked.
This
This
the
is
one
the long working out of
and then
and then
problem
problem 5
is
is drawing vector pictures of the spin echo.
we've
We've talked about the spin echo a number of times, so hopefully problem 5
you're
you're happy with. Let me see if there are questions about problem 5. So delta is 250 microseconds. Omega is 1 kilohertz. What's the rotation angle during delta? During the period that was delta.
we have
We're going to have transverse X magnetization at the Y pulse. Where will it rotate to in the period in the time delta? By the way to find that. Delta
is 250
is 250 microseconds. Omega
is
is 1 kilohertz.
What's the
What's the rotation angle?
Pardon?
Pardon?
Pi over 2.
Pi over 2.
Or if we just
multiply hertz times time,
this will be
1/4. And we realize since we're working in hertz, that's 1/4 of the circle, which is pi over 2, or 90 degrees.
So
So the magnetization
after
the pulse is on the x-axis. After the first delay delta, where is the magnetization going to be?
starts
on x, rotates around z towards plus y. X will rotate towards plus y.
So
after delta, we're going to have IY magnetization. And then we apply a 180 degree X pulse. What happens to it? Goes to minus IY. And then there's another period delta. Where does the magnetization end up?
on IX.
on IX.
Minus
Minus IY will rotate towards IX.
So the
So the
magnetization
magnetization started on IX after the 90-degree pulse.
during
During the first period delta,
it
it
rotated
rotated to the y-axis.
The
180-degree pulse flipped it over
to the
to the minus y-axis,
and then it rotated
and then it rotated back to the plus x-axis.
So we
So we could draw a little picture of that, of course,
that's
that series.
And now
we want to know this next problem.
Because
We have some spin
on resonance,
on resonance,
and another
and
spin
then
that's
another
off
spin that's off
resonance,
resonance by some amount of omega.
And now we
apply a pulse,
and
and
the
the
pulse
pulse applied on resonance is going to be a 90-degree pulse.
on resonance.
On
The
resonance,
only field is
the
omega
only field is omega 1,
Omega 1
so omega 1 times tau p
is pi
is pi over 2.
off resonance.
Resonance,
The spin
the
sees
spin sees the effective field,
so its
so its rotation angle
is
is alpha,
and it's
the effective field times tau p. Also has the same length for both spins.
The
The
pulse
pulse on resonance will transform IZ magnetization into the transverse plane.
Off resonance.
Off resonance, we don't want to generate any transverse magnetization.
So what has to be
true of alpha?
We have
Z magnetization.
We're going
to apply a rotation
such
that there's no transverse magnetization left after we're done with the rotation. What has to be true about the rotation angle?
Has
It has to be some multiple of 2 pi.
So we
So we come back where we start.
So
Alpha has to be equal to 2 pi.
So then
the question becomes,
given that we know
omega, capital Omega, we know the offset,
how do we
determine
what
omega 1 needs to be?
How do we
arrange this
for that to be the case?
So
Tau p
is pi over 2 omega 1.
So I can
get rid of the tau p here, substitute in.
So
omega e times pi over 2 omega 1 is equal to 2 pi.
The pi's cancel.
And I have omega e
equals 4 omega 1. And now
omega e is the vector sum
of
capital omega and omega 1.
So
this is, its magnitude is the square root
of omega squared plus omega 1
squared,
and
and that has to be equal to 4 omega 1.
So
So how do I solve this
for omega 1?
for omega 1?
How do I
How
solve
do I solve that equation?
What do
What do I do first?
I square
both sides, right?
So
So when I square both sides,
I
I
have
have omega squared plus omega 1 squared equals 16 omega 1 squared,
or omega squared
or omega squared is 15 omega 1 squared. Um,
and
and omega 1 is equal to omega
divided by the square root of 15.
divided by the square root of 15.
So if I
So if I
know what
capital omega is,
I can
I can calculate what I need omega 1 to be
for
for this magic trick to happen, and I get a 90-degree rotation on resonance
and
and a null off resonance.
This is the poor
This is the poor person selective pulse.
This is what
This is what gets used all the time for us for carbon-13,
where the
where the carrier is put at the alpha carbons,
and you
and you want to have the null
at the
at the carbonyls.
So
So
you just have to calculate
the frequency difference between the center of the alphas and the center of the carbonyls,
and then we
can calculate how to set omega 1, so that if we apply 90-degree pulse at these C alphas, nothing happens to the carbonyls. That's true for a 90-degree pulse. You should be able to go back then and answer the question, suppose we do a 180 on resonance, and we want a null at the off resonance position. So if you go back and do that, you'll discover the criteria is now different for setting up this trick with the 180s. But I'll leave that for you.
But this
gets used all the time if you look at an HNCO experiment, for example. The carbonyl pulses will be adjusted to satisfy this, so that you don't hit the C alphas when you're applying a 90 to the carbonyls. So this last one, is that the last one on here? I'll leave problem 7 for you to look at in the notes. Because it's kind of like the problem we already did. Here's a numerical calculation though. We use composite pulses. Pulse sandwiches, more than one pulse, to try to get better behavior. So this was a composite pulse that's supposed to be generating more transverse magnetization as a function in this setting of the pulse length. So it's not set to be exactly 90 degrees, or you could think of it as something that's resistant to B1 and homogeneity, because the B1 field isn't completely uniform with the sample. If you think you're doing 90 degrees, well, some parts of the sample are saying 90, other parts are saying 95 degrees, others are saying 85. So the solid line shows the result for just a single 90-degree pulse. You get perfect magnetization transferred to the transverse plane if the pulse length is exactly 90, but obviously short of 90, you leave some Z magnetization behind, and if it's greater than 90, you invert some of the Z magnetization. And now here's a numerical calculation for the composite pulse that I gave you in the problem. And you can see this flat section means that over some net rotation angle, you put all the magnetization in the transverse plane, even if the rotation isn't nominally 90 degrees. So this has better performance in the sense that all the magnetization gets into the transverse plane, even if there's B1 homogeneity to some degree. So as shown here, that would be it's like more than 30 degrees variation in the rotation angle, and still all the magnetizations in the transverse plane. These composite pulses usually don't come for free, because now this is the phase of the magnetization in the transverse plane. And the problem here is that is very nonlinear. So the phase effects of this pulse may be very complicated to deal with. And it's hard to find short composite pulses that have good performance in all aspects. You can improve them, and we can think of how do we add another pulse into the sandwich to try to improve the phase properties. When we add in another pulse, now everything gets longer, so there's more relaxation losses. It's harder on the probe to bring more and more RF in. Might be hard on the sample to heat it. So the box that you're in can be tight. You're trying to improve performance without suffering too much from all these other effects that are going on. On the other hand, if we're saying our goal here was to null Z magnetization, maybe there's an experiment where we just want to make sure that we null Z magnetization. And then maybe we're going to apply gradients to destroy all the transverse magnetization. In that case, this is pretty good, because we don't care about the transverse magnetization anyhow. And now we null Z magnetization, independent of any B1 homogeneity. So the literature has hundreds of composite pulses. And which one might end up using might depend on the particular application. But anyway, it also makes the point that these days the problem works out kind of mathematically here what the result is. But of course in the modern age, it's pretty easy just to make these kind of graphs and look at what happens rather than staring at equations. But what I wanted to do was problem 9, just 10. So here is a sequence for doing actually what I want to do. Let's do this one. So we're going to do a 90 degree pulse, X pulse. Wait a little bit, and then a 90 degree minus X pulse. And now we imagine
that we're
on residents
that the
water
water
signal
signal
is
is
huge.
and
And
over
over
here,
here,
at some
at some
offset,
offset,
are the
are the
NHs.
NHs.
And we
And we want to generate transverse magnetization in the NHs
and
and
leave
leave
the
the water
magnetization
magnetization on the
Z.
Z.
So for
So for on residents with the water,
it's
it's easy to see what happens to the water.
The
The
90
90-degree pulse
puts the
puts the water
into
into
the
the minus y-axis.
Nothing
Nothing happens because it has no chemical shift on resonance with it.
And then the
And then the
minus
minus x moves it back up to Z.
So for
So
the
for the water,
we
you rotate down and then rotate back.
So the
The water will be on Z and be like that.
What
What happens to the A minus? So after the 90-degree pulse, right, minus IY magnetization.
and then
during the period of delta,
we'll get
we'll get chemical shift precession, so minus IY cosine omega delta
plus
plus IX sine omega delta minus Y rotates towards plus X.
And now
And what happens after the
second
second pulse?
What does
What
the
does the minus X
pulse
pulse do to the minus IY magnetization?
You can
You
think
can
of
think of
it
it as a pulse around X minus 90.
goes to
Plus Z.
a minus
Minus
my
my fingers along the
minus
minus X axis,
and my
my
thumb
thumb
along
along the minus X axis, my fingers on the minus Y axis. Rotates to plus Z.
So
So
you
I end up with
I
IZ
cosine
cosine omega delta.
and nothing
And nothing happens to the IX.
So my
So my transverse signal is proportional to IX sine omega delta.
How
How should I set delta?
What do I want?
What do I want the product omega delta to be equal to?
Pi
Pi
over
over 2.
So
I set out of room.
So I
So I set
omega
omega delta
equal
pi over 2.
or
Or
if I
if I divide both sides by 2 pi, I can get the frequency units.
nu
Delta
equals
is
1/4
1/4,
or
or
delta
delta
1
1 over
or nu.
4 nu.
So I
So I measure the
frequency
frequency difference between water and my amide hydrogens, calculate delta,
and then
and then I have a simple water suppression scheme.
It doesn't
It saturate the water,
It leaves
leaves the water on Z.
So this
So this is called a jump return sequence.
And
Probably, I don't know, must have by now 2,000 citations in the original paper.
a pretty
A pretty simple idea
that
that turns out to be actually quite useful. Okay, I have to run off meetings. I will post these,
the answer key on
the answer key on Courseworks. And
send it to Mike so that
send it to Mike so that the people who aren't registered at Columbia can get a hold of it.
and then I'll also
And then I'll also
the
post
next
the
problem.
next problem set. Oh, yes,
I
I
forgot.
forgot to do that. Post
Can
those.
I ask you today if you were an update on that?
No,
No,